Hey guys, today we're going to talk about the law of conservation of energy. In particular, we're going to talk about how to use it to do some calculations, some useful calculations. So, quick review. What is the law of conservation of energy? It basically says that energy can never be created or destroyed. It can only be transferred or transformed. So, energy cannot be created or destroyed. Basically, that's why we can have no perpetual energy machines. We can't create our own energy. We can only use energy that's currently stored in different forms. Energy can be transferred from one object to another. Sorry about the space between those letters. That should be one word. Or it could be transformed. And transformed means actually changing the type of energy. So you can go from kinetic energy to potential energy. You could go from gravitational potential energy to a falling object having kinetic energy. You could go from an electrical battery having electrical potential energy, moving a toy car which now has kinetic energy. So it can be transformed into different types. Okay, so let's look at this in a little bit more specific situation. If we have a skater on this ramp, when they're very top, if they're at the top of the ramp and they are not moving, their kinetic energy is 0. But we all know that they do have energy. They have stored energy in the form of gravitational potential energy, which we could calculate with the equation GPE equals mass times gravity times height. And then as the skater goes down the ramp, the gravitational potential energy the skater has goes lower and lower and lower as the height goes lower and lower. But they start going faster and faster and faster as they get down the ramp. So the kinetic energy starts increasing as the gravitational potential energy decreases until finally you get to the very bottom. At the very bottom, the skater is going to reach their max speed. Okay? This doesn't say anything about being fast or slow, just we know it's the fastest speed they will reach. And we know that their gravitational potential energy at the very bottom will be 0. So all of the gravitational potential energy from the top is now converted into kinetic energy at the bottom. Now, if this is a frictionless track, or if the friction is so small that it's basically negligible, it doesn't matter, then we can make an important assumption. We can assume that the kinetic energy at the bottom of the ramp must be equal to the gravitational potential energy at the top of the ramp. Okay? Remember, energy can't be created or destroyed. If no energy is lost to heat due to friction, then the total amount of energy up here must be same as the total amount of energy down here, even though they're different types of energy, kinetic energy and gravitational potential energy. And this allows us to do a lot of calculations. Now, really quick, what is the case if there is quite a bit of friction on this track? In that case, the total energy down here is still the same as it was up here, but it's not all kinetic energy and gravitational potential energy. Instead, much of that energy will be converted to thermal energy because of friction. So both the green bar and the blue bar would get smaller, and thermal energy here would increase the more friction you had. But for calculations in this class, we're going to assume that it's either frictionless or nearly frictionless, so we don't have to worry about friction in our calculations. So, first problem. A 5,000 kilogram coaster is released 20 meters above the ground on a frictionless track. What is the approximate speed at ground level? Okay, so they asked for the speed. And the only way I know to calculate speed is with my kinetic energy equation. Kinetic energy is equal to 1/2 the mass times the velocity squared. But they didn't give me a velocity. I know the object's mass. However, I can recognize that what they did give me is enough information to calculate its gravitational potential energy at the start. And we know that gravitational potential energy equals mass times gravity times height. So let's calculate that. GPE equals mass times gravity times height equals 5,000 kilograms times 9.8 meters per second squared times the height is 20 meters above the ground. So it equals, let me punch this in my calculator, 5,000 times 9.8 times 20 equals 980,000. This cart has 980,000 joules of potential energy at the top. And again, if I'm not losing energy to heat, energy that radiates off into space, then the energy at the bottom, at ground level, must be the same as it was at the top, which means that at the bottom I have no gravitational potential energy. At the bottom, they would all be kinetic energy, and my kinetic energy would equal 980,000 joules. Well, now I can come back to this equation, and I can calculate my velocity, which is what the speed, right, they asked for in the first place. So, kinetic energy is equal to 980,000 joules. Therefore, 980,000 joules is going to equal 1/2 times the mass of my cart, which is 5,000, times the velocity of my cart squared. Therefore, 980,000 is going to equal 2,500 times velocity squared. I'm going to divide both sides by 2,500. So 980,000 divided by 2,500 equals 392. Therefore, I've got to go up here, sorry. Therefore, 392 is equal to velocity squared. The opposite of squaring something is the square root, so I'm going to take the square root of both sides. Second square root of 392 is equal to 19.8. So 19.8 would be a rough estimate of my velocity at the bottom of the track, and that's going to be 19.8 meters per second. So what's the closest here? 20 is pretty darn close to 19.8, so 20 meters per second would be my approximate speed at ground level. Okay, a 50 kilogram boy is jumping off a diving board into a pool. The diving board is 3 meters above the surface of the water. How fast will the boy be going when he hits the water? So let's make a quick sketch here. We have a diving board up here with a person on it, and it's roughly 3 meters to the water surface below. So again, they're asking how fast will the boy be going when it hits the water? And immediately I can recognize that they gave me a mass and a height. They gave me enough information to calculate his gravitational potential energy up here. I know that when he hits the surface of the water, all of that gravitational potential energy will have been converted to kinetic energy, and I'll be able to calculate his speed. So I got to start by calculating total gravitational potential energy when he's standing on the diving board. Gravitational potential energy equals mass times gravity times height. So gravitational potential energy equals 50 kilograms times 9.8 meters per second squared times 3 meters. 50 times 9.8 times 3 is equal to 1,470 joules. Now, that is the gravitational potential energy at the top. We know that all of that will be kinetic energy at the bottom, so I know at the bottom that kinetic energy will also equal 1,470 joules. Remember, this is only at the very bottom, just before this diver hits the water. So I know that kinetic energy equals 1,470, and I also know it equals 1/2 mass times velocity squared. Therefore, 1,470 equals 1/2 times mass of 50 kilograms times velocity squared. So 1,470 equals 25 times velocity squared. Divide both sides by 25. 1,470 divided by 25 equals 58.8. And remember to take the opposite of something that's squared. We got to take the square root, so we take the square root of both sides, and we get that velocity equals the square root of 58.8, which equals 7.66 I'm going to round that to 7.67 meters per second. That would be his velocity when he hits the water. Alright, last problem. A bouncy ball that weighs 0.1 kilogram is bounced off of the floor. As it leaves the floor, it's traveling 12 meters per second. How high will the bouncy ball go before it begins to fall back down? So this question is just the opposite of the last two we've done. In this case, they give us the mass and the speed instead of the height. In other words, they give us the kinetic energy as it leaves the floor. And then they ask us how high will it go? Well, similar to the last situation, if this is the floor and this bouncy ball is just headed for the ceiling going 12 meters per second, we can calculate the kinetic energy at the bottom, and we know that will all slowly, the kinetic energy will get smaller and smaller and smaller the higher it gets, until at the very top, kinetic energy will equal 0, and all of the original kinetic energy will be gravitational potential energy. Okay? So, I have to find out how much energy does it have to start with, and that's kinetic energy. It starts with kinetic energy, which is equal to 1/2 mass times velocity squared, which is equal to 1/2 times our mass of 0.1 kilograms times our velocity, which is 12 meters per second squared. Remember not to forget this 1/2 in the equation. So it equals 0.5 times 0.1, which is 0.05, times 12 squared is 144. 0.05 times 144 is 7.2. So this bouncy ball starts out with a kinetic energy of 7.2 joules. We know that the gravitational potential energy at the very top will equal the kinetic energy at the very bottom, so we know that the gravitational potential energy at the top will equal 7.2 joules as well. Therefore, 7.2 joules will equal the mass times the gravity times the height of the bouncy ball at the top. 7.2 will equal the mass of 0.1 kilograms times 9.8 meters per second times the height. 7.2 joules will equal 0.1 times 9.8 equals 0.98 times the height. I divide by 0.98, cancels, and therefore 7.2 divided by 0.98 equals 7.346, so I'm going to round that to 7.35. 7.35 equals the height, and therefore height is equal to 7.35 meters in the air. That's how high the bouncy ball will bounce. Okay, that's it for this. Those two different types of calculations are the only ones you guys will have to do for the test. So anytime you get stuck on those, come back, watch this video, and review them. All right, that's the end of this video. Thanks for watching.